I think I'll say that at the end, but very, very much.
Yeah, for sure. Thanks everyone for coming. Welcome. I think this is like the third meetup we've hosted in this space. It's great to see the room filled with tech enthusiasts. So if you're not familiar with Tegus, we are a financial research platform. We help investors make better investment decisions through qualitative and quantitative insights. We do that a lot through expert interviews, which means we have a lot of qualitative data with a lot of words, which is very relevant for today's talk. So we have some cool stuff happening here in terms of machine learning. We're building with Python, we're building with OpenAPI. And that brings me to our speaker, our VP of machine learning, Michelangelo D'Agostino. I hope I said that right.
It's pretty close. Yeah. All right. Thank you for doing that on 10 seconds notice, Alex. All right. Yeah. Hey, everyone. It is great to be here. I also have not been in a room this full of people in a long time. The last in-person talk I was supposed to give was, I think, April of 2020. So we're about to find out together how rusty I am in person talking. But I'm excited to tell you about building with large language models. I think we all kind of have this feeling that we're living through a really interesting time to be doing machine learning right now. Interesting, potentially historic, depending on what your point of view is. But basically, like, we're living in a time where it feels like everything is moving faster and faster, and there are advances coming out every week and every month. AI and ML are sort of just skyrocketing. So being a good data scientist, I didn't want to just like have that feeling. I wanted to actually have some data. So I went to Google search trends and I pulled up just the search trends around AI and GPT for the last, I think this is the last 12 months. And you basically see, starting around last November, December, largely catalyzed by the release of ChatGPT, things have gone through the roof. So the AI search trend volume has almost 10x'd from back in April. Now, Google search trends is like on a relative scale. And so they always tell you it's important to like put some other comparison point in there. So I added this in there just as a reminder that, like, even though we feel like it's kind of amazing what's happening right now, like AI is still not a match for Lionel Messi in the World Cup. That said, there is something pretty amazing happening right now. And it's my job to try to like keep up with what's going on. And I feel like I'm having a pretty hard time doing it. So if you kind of like Rip Van Winkle, you took a nap like 6 months ago, 12 months ago, where you haven't been paying attention to NLP for like the last couple of years. And then all of a sudden you woke up like in the last couple of months and you were like, whoa, what is going on? Like the world feels really different now than it did the last time I was paying attention to NLP a couple of years ago. I've tried to gear this talk for you. So I'm going to talk at a really high level and probably also a really rapid clip about all the stuff that's kind of happened in the last couple of years in NLP that has helped this to skyrocket. And I'm also going to put a bunch of references in here. I'll share the slides afterwards if you want to read more about any of the references I stick in here. So how am I going to do that? So first, I'll do a really quick, usual, like, well, actually not so usual, who am I spiel. And then the meat of the talk is really going to be two sections. So first, what are large language models and what can they do? And it's largely going to be a picture-based sprint through like a bunch of research papers for the last 5 years. After that, we might need a quick break. So I'll do a quick word from our sponsor, like what we do at Tigas, and in particular, how we're using large language models. And then the second meaty part of the talk is going to be more practical and like more code-based for kind of patterns and tools for building things on top of large language models. So if you're kind of like a theory or a research person, part one might be basic for you, but part three might be a little interesting. If you're more of a practical person, part three is probably for you. And if you're both, then you're probably Derek in the background, and just don't ask me any hard questions afterwards. All right, so let's dive into it. So normally at this part of the talk, I would give an intro to myself. I would say like, hey, I'm an ex-physicist. I've been doing machine learning at startups in Chicago for the last 10 years or so. But I thought a fun way to do this would actually be who I am according to large language models. But as you'll see, it turned out to be a who I am not according to large language models. So I asked Google Bard, which is Google's ChatGPT competitor, to tell me about myself. And first, it said that I work at Tegus, which is not a data science and engineering firm. It said I graduated from the University of Chicago and the University of Oxford, two fine institutions that I did not graduate from. And also that I wrote for Wired magazine, which I did not do. Bard will return several drafts to you. On its second chance, it said that Tegus was a machine learning consulting firm, which we are not. And it also, this is great, but it's not true, that I co-authored a book called Data Science for Business. All right, so Google Bard, we know it's maybe not as cool as OpenAI, so I figured I would go and ask GPT-4 about me. So it has a very specific birthday and city, both of which are not correct. My favorite one is that I co-founded a data analytics and consulting firm called Blue Labs, which is actually the main competitor for a company I did work at in the past, which I did not co-found, and that I served as an advisor to the US Digital Service. And finally, as you'll see later, I'm going to talk about some of the open source versions of these models. And this is maybe my favorite, that I'm actually Michelangelo, the Italian sculptor. All right. So this is kind of funny, right? Like large language models gave me credit for writing a book that I didn't write, co-founding a company that I didn't co-found, advising a government agency that I didn't advise, and for being a dead Renaissance sculptor. So it's kind of funny, right? But you can imagine a scenario where the things that are not true are actually very not funny. And the main reason I bring this up is because I think it's useful context to keep in mind for the rest of my talk. So the rest of the talk is going to be genuinely like excited about where this is going and all the things that we can possibly do. But there are actually real problems here. And if you're building things on top of this stuff, it's really important that you think about these and engage with these issues and figure out how to mitigate them for your exact example. So I thought this was a little bit of a funny but sobering way to start, at the risk of perhaps undercutting the rest of my talk. All right, so now I'm going to dive into like, what is a large language model? What is the language model that was producing those answers about? So again, I figured I would go and I would ask ChatGPT. So ChatGPT says, a large language model is an artificial intelligence system that has been trained on vast amounts of text data to generate human-like language outputs. It uses deep learning algorithms and natural language processing techniques. So there are a few key points here. So first, these large language models are deep learning models. They're deep neural network models. They've been trained, or often you hear people talk about them having been pre-trained on huge amounts of text data, and they generate human-like language. So these are, you've probably heard the term generative AI. So models that generate new things, that is what a large language model is. That's a fine definition. I still kind of actually prefer a lot of things about the human-generated Wikipedia definition. So Wikipedia goes a little more in depth, and it highlights that these neural network models have billions or typically hundreds of billions of weights. So they're very, very large neural network models. The technique that we'll see in a second for how they're pre-trained is called self-supervised learning. So it doesn't need golden example labels, human annotated labels. And large language models emerged around 2018. And then it goes on to actually talk about maybe the most interesting part of this, which is that for reasons that I believe no one actually understands, these large language models, which are trained to be fancy versions of autocomplete, show what people often talk about as emergent abilities. So basically, as you make these models larger and larger and you train them on more and more data, they suddenly acquire abilities that were not programmed in the first place. And these are often called emergent abilities. So for example, no one taught these models to do arithmetic. No one taught them to pass college level exams, to do various things like unscrambling words or understand, translate from one language to another. These weren't explicitly programmed into the model, but they sort of emerged as the models got bigger and bigger. So this is an example figure from the Wikipedia entry where on the X, these are a bunch of different kinds of tasks like doing arithmetic or answering questions and answering questions. Question and answering in Persian, unscrambling words, et cetera. And on the x-axis is how big the model is. And you can kind of see that like as the model gets bigger and bigger, all of a sudden it sort of spikes up and it gains the ability to do all these ancillary tasks that the models were not trained to do in the first place. And this is both what's made these models super interesting and exciting because they can do they seem to gain the ability to do lots of general purpose things. But I think it's not an understatement to say no one actually understands why this happens, which is interesting. Okay, so the Wikipedia entry says these generally emerge around 2018. So what happened in 2018? So there are basically two things that happened in 2018. There's this famous blog post that came out around that time called NLP's ImageNet moment has arrived. So if any of you do computer vision, you're probably familiar with ImageNet. It was a very, very large data set of images with labels on it. And if you worked in computer vision, people would train very large models on top of this data set. And then those models, pre-trained models, would become very generally useful for other tasks downstream. So people would then just like sort of tweak them a little bit for their specific purposes. So around 2018, a lot of folks doing NLP realized that they could do similar things in natural language, that they could pre-train very large neural network models that would be generally useful for other purposes downstream. And this blog post talks about language modeling being one potential way that you could pre-train these models. And again, language modeling is just the task of predicting the next word, given all of the words that came before it. So if you have the sentence, the best thing about AI is its ability to, your completion could be, learn, predict, make, understand, etc. And when this blog post came out, actually, it wasn't clear that language modeling was going to be the best way to pre-train these models. People were doing lots of different things. This blog post makes the case that actually language modeling is perhaps a really good way to be doing this, because in order to predict the next word in a sentence, you have to learn lots of rich things about language. You have to learn about grammatical rules of syntax. You also have to learn things about what words mean, etc. And maybe this kind of dumb looking language modeling task would actually learn really useful things. So that was the first thing that happened. People started pre-training models on very large sets of data in natural language. And then the second thing was this paper, which came out at the very end of 2017, called Attention is All You Need, which introduced a new kind of neural network model that basically caught like wildfire and took everything over in the subsequent years. And this paper introduced what's called the transformer architecture. So I'm going to talk about this at a very high level. I'm not going to go too in-depth into it, but if you're interested, there's this really great blog post called the Illustrated Transformer that has a bunch of pictures and kind of an intuitive explanation of what the model is doing under the covers. So this paper was a machine translation paper. So it was starting from French and wanting to translate a sentence into English. And the transformer is the model in the middle that does that. So if you go a layer deeper, it's made up of two parts. There is an encoder part and a decoder part. And then if you go one layer deeper, each one of those parts is made up of a repeating. Ooh, can you actually see these a little bit? They're a little small. Sorry about that. Each one of the parts, the encoder and the decoder, is made up of a series of repeating identical subunits. So then if you break that open, what's inside one of these tiny little subunits, there is a part called self-attention, and then there is a normal neural network part on top of it. And it's this self-attention part that was the innovation of the paper, and that has become kind of the foundation of all of the subsequent generations of these language models. So what is self-attention? What does it actually do? Basically, it's just a way of looking back at all the words that came before the last word that you're in your sequence, and sort of packaging it up in a form that's really useful to predict the next word. So if I go one layer deeper than that, what actually happens is each word emits two vectors, two kind of arrays of numbers. One is called a query and one is called a key. And the query sort of expresses what kind of information am I looking for as a word. So for example, I took this from an interesting video I'll link to later. But for example, like the query could be, I am a pronoun and I am looking for other proper nouns that came before me, because that would be useful for me to know about. And then the key is an expression of what I contain. So another word might say, hey, I am a proper noun. And what happens is you define kind of an affinity between two words based on how well aligned that query and the key are. So for example, like if you're a pronoun and you're looking for the proper nouns, and the other one is a proper noun, then they might be very aligned and you could pass information between them really strongly. So the pronoun could learn a lot about the proper noun that came before it. But the key is that this is all learned. So you don't have to program in, I am a pronoun looking for proper nouns, or I am a proper noun. That's all sort of learned as part of the training process. And the visualization down here shows kind of those attention weights for the sentence, the quick brown fox jumped over the lazy dog, didn't it? And you can see for quick, like the words that it pays the most attention to are brown and fox and jumped, because those are what quick is sort of modifying. And then the pronoun it down here is sort of paying most attention to the word fox that came before it, which is the proper noun that it is a pronoun for. And so this is what really was useful about attention. It let words pay attention to the most useful other words in the context and learn that in a data-dependent manner. So this was the attention is all you need paper. And if you look at that architecture, the encoder decoder I mentioned, it doesn't look like if you've actually read anything about GPT or the other language models that have come after it. And that's because it was in this machine translation context where you took a sequence in and tried to predict another sequence. Subsequently, people realized actually this was useful for a lot of different things, and you can have an encoder only transformer model. So if you ever played around with BERT or Roberta or Distelbert or all these like BERT families of models, those are called encoder only transformers, just the first part. And then what's most relevant here is that GPT and most of the current generation of large language models are decoder only language models. And really all that means is that if it's a decoder only model, you're only allowed to calculate the attention for words that happened in the past, because you're trying to predict the future word. So if you see these weights, they only go backwards towards words that came before. Whereas this encoder only model can look sort of into the future or backwards. And so that's not useful for predicting the next word because you don't know the future, but it is useful if you're doing things like sentiment analysis or trying to classify a sentence or something like that, where you actually have the whole sentence ahead of time. But for all of the subsequent language models, all the GPT models, these are decoder only transformer models. Okay, so those are the things that happened in 2018. So what has happened since 2018? So I'm going to talk about 3 important things that happened since 2018. So the first is literally just that people continued to make these models larger and larger and larger and larger. So it's a little bit hard to see on here, but the x-axis is year starting in 2018 on the left, and it goes up to, I think it's 2020 on the right. And this point up here is GPT-3, which was 175 billion parameters. So you can see this exponential growth in just how large people started to make these language models. This is a log scale, right? So remember, like a line on a log scale is an exponential pattern, which shows GPT-3 here, and then extends on to some of the later models. GPT-4, which came out, I guess, last month, under a month ago, reportedly has 1 trillion parameters. And so in the last 5 years, we've gone from models having roughly 100 million parameters to models that have 1 trillion parameters. So that's the first thing, just training larger and larger models with more capacity on more and more data and seeing these new abilities emerge from them. And then the second thing is an advancement that actually kind of is what blew everything up in November when ChatGPT came out, which is this idea of instruction fine-tuning large language models. So large language models, right, they're tuned to predict the next word. And actually, if you just look at the raw output of a lot of these large language models, they're not super impressive. And what really got people impressed with ChatGPT was that people found ways to fine-tune large language models to sound more like natural human language, or to produce more chatty responses that seemed more pleasing, I guess, to people to converse with. And that came from this paper that OpenAI released, I guess, just about a year ago, which introduced 2 techniques, one called supervised fine-tuning and one called reinforcement learning from human feedback. But the core idea of both of these is that you can take a much smaller number of labeled human examples and then use them to tweak these big pre-trained models to get output, which is actually much, much better. And that's sort of what caused everything to blow up in the fall when ChatGPT was released. So I won't go in too much detail into this, but I'll just explain it a little bit of a high level, what happens here. So on the left, basically is this fine-tuning process where you ask a bunch of humans to generate responses to a prompt, and then you use that prompt to fine-tune your original large language model. So it starts to generate language which is more like the language that a human would generate here. And then in the second and third part, it uses a technique called reinforcement learning, which I'm really not going to go into. But the idea mainly is that you can learn, you can train your model to produce things of higher and higher reward. So reinforcement learning is what people use to train like Atari video game players and robots and things like that. So again, you start with a prompt, you generate a bunch of different possible model completions of the prompt, and you ask a human to rank them. And based on that ranking, you train a model to give you a reward. So here the human ranks D the best, so the reward you get for predicting D should be higher than predicting B. And then you throw it into one of these reinforcement learning processes where it, again, tweaks the model weights such that it's more likely to give you things with high reward, which are things that a human really, really prefers. And so that is reinforcement learning from human feedback. There's an interesting video I linked to here. But these two techniques are basically what allowed ChatGPT to come out in the fall, which produces text that is much more like what a human would say in a conversation. All right, so last thing that's happened to end sort of the overview of the research world is it's kind of a crazy thing, but giving large language models access to external tools and APIs. So this is one of the things that is a potential solution to this issue of language models saying things that are factually incorrect. If you give them access to various APIs and things that know about the world, they may be able to incorporate that in a better way. So there are two interesting papers I linked to here. One is called React, which is a method I'll show in the next paper, a very actually seemingly really dumb way that seems to work to connect language models to external tools. And then one from Facebook from just a couple months ago called Toolformer, which is language models teaching themselves to use tools. So the idea is actually really, really simple. You tell the model to behave in a certain way. So express a thought, take an action, and then pause, and then get the observation from your action. And this is from a really amazing blog post. It's like 100 lines of Python where the guy implements one of these connections to external tools. So you tell the model, you have three things that you can do. You can run a calculation using an external calculator, and I'll give you the answer back. And if you want a calculation, reply with calculate and then what you want. You also have access to Wikipedia. If you want an answer from Wikipedia, do Wikipedia : and then what you're searching for. And then this guy also hooked up search to his own blog. And so here is an example of what a session looks like. You ask it a question, what is the capital of France? The model expresses a thought, I should look up France on Wikipedia. And then it outputs an action in this structured format that says Wikipedia : France. And at that point, you sort of interrupt the execution of the model and you grab this and you go out and you like run a Wikipedia search. You make an API call, you run a Wikipedia search, and then you get the text back. And then you say, okay, the observation is the text that I got back from Wikipedia. France is a country, the capital is Paris, blah, blah, blah. And then the language model can incorporate that information in the answer that it gives. And so then you then output the capital of France is Paris. So this is sort of an example given to the model of how you want it to operate. And it actually often works very well. I'll show some examples of that later. And this is largely behind what was arguably maybe the most important announcement of the last couple of months that I think went under the radar because it happened 2 weeks after GPT-4 came out. But OpenAI announced a whole ecosystem of plugins, which is basically kind of like an app store for GPT that gives the GPT model access to all kinds of external APIs and tools, like I just mentioned, and allows the language model to call out to those things and incorporate the answers back into its responses. And I just linked to a really, really interesting blog post on the potential ramifications of that. All right, that is a lightning introduction to what's happened in research in the last 5 years. Are there any quick questions before I go on about any of that? Yes. Yeah. I think it's fair to say that most people were surprised by the stuff that happened with ChatGPT in the fall. I think people had been paying attention for a long time that these models were getting bigger and bigger, that they were getting emergent abilities, that they were able to do general things that you used to have specialized models to do before. I think that was kind of obvious to people. But I think everyone was kind of caught off guard in the fall, partly by like people's response to the product that they released. Yeah, I don't know. I think everyone was surprised, but I'm not really sure why people were surprised. Like, I guess the model was that once it was instruction tuned, it was a little bit better maybe than what people were expecting. But I think it was more just the general public who hadn't been paying attention, like what their reaction was. And then this like feedback loop sort of happened where it was like, oh, my mom's talking about this stuff. This is really exciting. Like, and it sort of fed on itself. Yeah. Yeah, I mean, I think like for people who've been deep into this stuff, like the techniques are, I think, familiar and not like, people have been reading these papers for a long time and understanding that this stuff was coming. I think probably what's different is the bridging the gap between like what researchers were doing and what's become very useful for people to do in the real world in companies. Like it's that was actually probably one of the other innovations of OpenAI, that they released this stuff via API for people to play around with. Like Google has these models. A lot of other places have models of similar scale to GPT-3. They just didn't open them up in the same way for people to play around with, I guess. Okay. Yeah. So what made these techniques go mainstream? I honestly think it was like releasing a simple web page that people could go to play around with. Because honestly, like the techniques existed, like people had examples of these working on their laptops, but it was something about this very simple interface that people could play around with that just generated this crazy response. I don't know. All right, let me take one more question and then I'll continue, and then we can do more Q&A at the end, I guess. Sorry, your hand was up earlier. Yeah. Yep. Yeah, I'm not an expert on the cost of training these models. I mean, so in some sense, like you can parallelize these models and it grows linearly with model size, but also the techniques have gotten a lot better from the beginning, like the optimizations. Also, like people have started developing specific computer chips for training these models, which changes things as well. So not just GPUs, but specific ones. So I couldn't tell you actually, like, but once it became clear that the models needed to get bigger and bigger and trained on like supercomputers, like folks really did start to optimize them as much as they could. So, yeah. All right, let me continue, and then we can do more Q&A towards the end. All right, so I'm going to break for a quick word from our sponsor and tell you just a little bit about Tegus and how we're using large language models. So Tegus is a fintech company, and we make a research platform for fundamental financial investors to research companies. So if you invest money for a pension fund or a hedge fund or a university endowment or something like that, you spend a ton of your time going really deeply researching companies. And that involves looking at tons of data sources. So maybe you read every single SEC filing on a company. You read all the things that their management team has said in public. You talk to experts. So these are people that might like use the product of the company or people that used to work at the company. Your job is basically to like collect and siphon and digest as much data as possible. And so at Tigas, what we're doing is building a platform that makes that really easy across a bunch of different sources that investors look at. So our bread and butter really started in this expert research area where we help connect financial analysts, financial researchers with experts about a company, and then they do a long phone interview. And when the phone interview is done, we transcribe the interview and we post it on our platform for any of our subscribers to look at. So for example, let's say you want to invest in Snowflake, you think it's a great database company. If you go on Tegus and you search, you probably see 200 interviews that really smart financial analysts like you have done about Snowflake in the past. You can read that stuff, you can digest it, you can get up to speed. And then if you still want to or you need to, you can ask specific questions, or you could arrange a follow-up interview to get your specific questions answered. But you're at least not starting from square one, which is sort of where the industry existed before, where everyone was sort of repeating the same phone calls over and over again. We acquired a company called Bansec about a year ago that aggregates and structures all sorts of text SEC filing data. And then I guess not quite a year ago, we acquired a company called Canalist, which helps to build Excel financial models for company performance. And so for the purposes of this talk, we actually sit on top of a giant mountain of text data. So all this SEC data, we have something like 50 or 60,000 of these hour-long investor interviews, which are, I don't know, probably 20 pages of text equivalent. And there are lots of things that we are using and are planning to use large language models for to help us. So the first, which is a thing we actually just released this week, is natural language summaries of our articles. So instead of like giving you no clue whether you want to invest time to read this very, very long transcript, we're actually using GPT-3 to generate a natural language summary at the top to give you an idea of what it's about before you actually want to invest in it. Alex, who graciously introduced me earlier, is working on a topic analysis, again, using GPT-3. So basically pulling out the set of unstructured topic tags for a transcript to enable search applications, and again, to give someone an idea about what a transcript is like. There are plenty of other things we've thought about. So we've explored using GPT to generate like a competitive set for a company. This is not something that's actually very easy to do. Like if you're starting to research company X and you don't know anything about that space, who are company X's competitors? All that stuff is buried in our expert interview transcripts, and you can pull that out in a structured way with these language models. Maybe the thing we're most excited about and we get the most questions about is building a chat interface on top of all of our text data so that you can go on and you can say, tell me about Snowflake's earnings last year, tell me about who Snowflake's competitors are, and just literally chat with this corpus of text data that we have, and many more. I think what's really happened over the last couple of months is these APIs have just caused people to sprout ideas left and right about things that we could build, which is really cool. All right, that's the end of the word from our sponsor. And now I'll get into kind of the more practical part of the talk. How am I doing on time, actually? Is anyone keeping track? Okay, all right. So this is gonna be a little bit more of the practical part of the talk, which is like, how do you start playing around with these models? And like, what are some things you should keep in mind if you're gonna try to build some things on top of models? All right, so the first thing, I'm gonna go over this kind of a little bit quickly, but the first thing is I wanted to talk a little bit about all the models that are out there and what some of them are and what you should keep in mind as you're thinking about models. So there are a couple key considerations to keep in mind. So the first is kind of model size, because as we've seen, performance tends to scale with the number of parameters in a model. That is sort of true, but there's also a consideration that the more data you train a given model on of a given size, the better it performs. The second thing is instruction. Has the model been instruction fine-tuned or not? We talked about instruction fine-tuning a minute ago, but those models are generally going to perform better at following instructions. And then the last pieces are sort of the commercial questions. Is the model open source? Can you play around with it? Are you even allowed to use it for commercial use, et cetera? And there's this benchmark called Helm that I linked to here, which is a really interesting in-depth comparison of a lot of these models, which you should check out if you're thinking about building stuff with it. Okay, there's a little bit of an eye chart, but generally for all of these, I put red stars next to the ones I think are probably worth looking into more if you are considering building. So at the top of the list are the OpenAI models. So up until November, GPT-3 was the largest of them, but was not instruction fine-tuned. The API that's called GPT 3.5 Turbo, that's the one that came out actually just last month, but that is the API version behind ChatGPT, which again is instruction fine-tuned. And then literally last month, I believe it was, GPT-4 came out, the largest of them all that is instruction fine-tuned and seems to perform a lot better. So all of these, of course, are open for commercial use, but they're closed source, right? So you're not going to learn anything about the internals really of what's happening there. So as a default, if you're thinking about building something, the ChatGPT API is the one I would start with because it's drastically cheaper than the other ones, and it seems to work pretty well. Two other vendors in the space that have models that are of similar size and people seem to report working really well as well are Anthropic, which was kind of a splinter of OpenAI. A bunch of OpenAI folks started a competitor, and their model is called Claude, which uses a different method of instruction fine-tuning, but it does have that fine-tuned nature. And then this Israeli company, A121 Labs, has a series of models called Jurassic, which also are very large and seem to perform really well. So those are 4 commercial models that you can get access to via API if you're thinking about starting to build with this stuff. Down here are sort of the open source models that are of this similar size. And they're interesting if you want to play around with some models in Hugging Face, but you can see here, none of them are instruction fine-tuned. So they're not going to give you output, which is quite as useful. Okay, so this slide is mostly useful to know about because these three models on the bottom are our bases, our foundations for the models that I'll show in the next couple slides as people have started to build truly open source instruction fine-tuned models. So maybe the one that's worth knowing about here is called Llama. That came out in February, and it was sort of like, I kind of like to think of Llama as Facebook's middle finger to OpenAI, because they were like, hey, we're going to release a fully open source model. It's not as big as GPT-3, but they trained it on much more data, and they claim that it performs as well as GPT-3. And so they sort of released it and open sourced it. I think, again, it's kind of a way to stick it to OpenAI a little bit. But the key thing about this model is that it is not, it's not instruction fine-tuned, but it's also not licensed for commercial use. It's only licensed for research use. So what happened after February was that two things happened. One, the academic community started to fine-tune that instruction, fine-tune that Llama model. And there's like a whole zoo of models that you'll see. Alpaca is one that came out of Stanford. Koala, Vicuna, Dolly is a Databricks one. I think someone might be giving a lightning talk about later. But the important thing about all of these is because they were based on Llama, which is not licensed for commercial use, none of them are licensed for commercial use, but they are instruction fine-tuned. So they're kind of useful for a research purpose. But then literally like in the last week or 2 weeks or 3 weeks, this stuff, I was updating this slide literally every 2 days over the last couple of weeks, because basically what's happened is that now there's literally a race to release a ChatGPT quality model that's both fully open sourced and licensed for commercial use and instruction fine-tuned. And I'd say literally within the last 2 weeks, there are probably 3 or 4 legitimate competitors, legitimate models that claim to do that. So Dolly is one from Databricks, where they trained it on this Pythia model that I showed on the previous slide, but they collected their own instruction tuned data set that is licensed for commercial use. Open Assistant is one that has a really interesting set of human demonstration examples they're collecting from a feedback forum. Stable Diffusion, which is the company behind one of the image models, I think it was just last week, announced a language model. And then Red Pajama is another really interesting open source effort that has a giant data set they're working with. So basically, like by the end of the year, there will be an fully open source, commercially licensed ChatGPT class model, if not much sooner. So if you're interested in running your own stuff locally, you don't want to use those APIs, these are the things I would kind of keep an eye on. And this is literally changing like every week right now. Okay, so that's kind of the model zoo. Like, how do you actually start to work with some of these models? So, it's often said language models are autocomplete on steroids, right? They just help predict the next word in a sentence. So to get them to do anything, you have to feed them what's called a prompt. Sorry, I'm gonna lose my voice today. You feed them a prompt, which is a bunch of text you give them at the beginning, and then they autocomplete that prompt. And what they autocomplete is sort of the solution or the answer to your problem. And so there are kind of 2 popular techniques for doing this. One is called zero-shot learning, and one is called few-shot learning. And in zero-shot learning, it's kind of like YOLO learning, I guess. You basically just ask it to do something without really giving it any examples of what you want to do. So here you just give it the text. I'll bet the video game is a lot more fun than the film. And then you ask it, hey, what's the sentiment of this? You don't give it any examples. And that can actually work. It can actually work pretty well. What often works a little bit better is what's called few-shot learning, where in the prompt, you actually stuff in a few examples of what you're trying to do. So you give it some examples of sentences, and then you give it what the sentiment is of that sentence. So here you give it 3 examples, then you give it the text, and then you ask it for the sentiment. So all of this stuff is like literally stuffed into the prompt. It's the text that the model is trying to complete, but you're sort of setting it up. You're sort of teaching it a little bit what you want it to do when you, in this few-shot context where you give it some of the examples ahead of time. Another technique people sometimes use is called self-consistency sampling, which again, since these models are probabilistic, you don't always get the same output when you ask it the same thing. And so here you just ask it to complete the same prompt many times, and you take the most likely answer. You take the majority vote, and that can sometimes help. And an interesting one, which often helps with sort of logical problems, is called chain of thought prompting. And here, this is really kind of hard to read, but basically it can be as simple as saying to the model, let's think step by step, like asking it to sort of show its work like you would a grade school kid in math class. And is this legible at all on there? Probably not. So here it feeds a couple examples in of the step-by-step logic that it wants the model to take. So it's like, this is a word math problem. Tom and Elizabeth have a competition to climb a hill. Elizabeth takes 30 minutes to climb the hill. Tom takes 4 times as long, yada, yada, yada. You get the idea. This is like the kind of thing that you ask, kids in grade school math. And you sort of prompt it to think step by step, like to basically to show its work. And when you give it examples of how to show its work, it's been shown that leads the model to do arithmetic problems much better, asking it to sort of think step by step. Okay, so those are some techniques for how you input things to the model. So how do you work with outputs of the model? I said that the outputs are just like the completion of all the text that you feed into the model. So there are a lot of hacky techniques people have used, like literally just regex parsing the output of the text. Or it can actually work to literally tell the model to output a nice format to work with. So you can ask the model to output JSON. You can ask the model to output Markdown. These are 2 examples from some work I've done where I asked the model to do entity recognition. So extract any company or product names from this list of text I'm going to give you. And your output should be a list of companies and products, 1 per line, starting with a dash. So you give yourself something that's really easy to parse. That's a strategy. But as this has matured a little bit, people have come up with other better ways to do that. There's an interesting open source package called Guardrails, which lets you sort of define a little bit of a structured spec for what kind of output that you want. And then it will check that the output of the model conforms to that. And it can retry and do various things if it fails that spec. That's worth looking at. Another interesting one is this project called Marvin, which these guys from Prefect are going to talk about a little bit later, so I won't talk too much about. But it's really kind of amazing that this works. Basically, like you put a decorator on a Python function. The doc string of the Python function is kind of the prompt, like what you want the function to do, but you don't actually fill in the code. The language model like generates the code and the output. And with this this type annotation, you tell it, hey, I want a list of strings. That gets the model to generate something of the right format. You actually will get an array of strings out of here. I won't talk more about it, but this is kind of an interesting way to generate structured output and potentially chain multiple language model calls together. Which leads me to my next topic. So as you're building these things, you'll quickly realize that like you're not just making one call to a language model to do one thing. You're going to make many, many calls, and you're probably going to chain them together and feed output from one into the other. Part of the reason for that is that these models tend to do better with simple instructions. So you might ask it to do something simple and then take that output and feed it into almost like a pipeline type thing. And the other reason is that you can only feed so much context into a model. So you can't just give it like 1,000 words of context. You have to break it up into little pieces. So that's called chaining. And of course, you can just chain things together in like regular Python code, but there are nicer ways to do that. So Marvin is probably a nicer way to do that. But what's become a little bit of a de facto way to do this is working with an open source package called LangChain. So LangChain is kind of a toolkit. It has a bunch of different pieces for working with large language models. But then it has this concept of chains, which lets you string multiple language model calls together. So it kind of looks like this. You define a prompt, which is, what is a good name for a company that makes blank? And blank is a thing that you're going to feed into this template. And then you make a chain to do that. And then you make a second prompt that says, write a catchphrase for the following company, blank. And then you make a chain for that. And then you basically construct a sequential chain where first you run this one, and then you take the new company name, the company name that it's generated for you, and you feed that into the second prompt. And what it looks like when you actually run this is, okay, so I've entered this simple sequential chain. Here's the output of the first thing. A good company, a company that makes colorful socks, a good name might be Cheerful Toes. And then that gets fed into write a catchphrase for the following company, Cheerful Toes. And the catchphrase is spread smiles from your toes. So this is a really simple, dumb example, but it gives you the idea how you could build up more complicated workflows in a structured way with these language models. LangChain also has support for agents. So remember I talked earlier about connecting language models to external APIs and databases and stuff like that. There's this amazing blog post with LangChain source code where this guy connects up GPT-3 to this external sports API. And it's really simple. Like he just literally defines a function that uses Python requests to get data from this sports API. And then you register the tool with LangChain. So you initialize an agent with the list of tools it has access to. And then remember I flashed the React paper at the beginning. That's the one that talks about like express a thought, then give me the action, and then I'll give you the observation of the action. LangChain has that built in, and it allows it to do things like this. So he asked the question, how many points are the Boston Celtics allowing on defense per game this NBA season? And how does that compare to their last season? And you can see what the model does. It says, okay, my first thought is I need to find the points allowed per game for the Celtics this season and last season. What's the action I should take? I should query this stats news site with the query Boston Celtics points allowed per game. Okay, so that happens. Then you feed in the observation. And the next thought, I need to find the points allowed per game last season. And then it queries the database again. It gets the answer. Thought, I need to calculate the percent change. Great, I have access to a calculator, and so on and so on. And then the final answer is the Boston Celtics are allowing 7.4% more points per game this season compared to last season. So that actually is the right answer. And it's learning to use this truthful database of sports scores. And it's literally this much code to actually do it with the LangChain framework, which is kind of crazy. So LangChain, it can run in kind of a verbose mode where it shows you all the intermediate steps. And so you do. So you as the developer, so the customer would input the top question, and you as the developer could have access to all of the internal thoughts in the middle because LangChain is outputting that. But you could choose not to show that to the user, and you could just display the answer. But this actually does get to an interesting user experience question with all this stuff, which is like, I showed you the thing at the beginning where all these models lied about me. Like, how do you get people to trust the results of these models? So some of it is maybe like showing the intermediate steps. How did it derive it? Like learning to cite the pieces of information so people can look at it. Like that's a very unresolved issue right now. Like what you want to show people. You probably don't want to just show the answer because people are gonna be like, the hell is this? Like, how do I know if this is totally made up or not? All right, and the last thing I'll mention is that LangChain is very early, but is wanting to have the concept of a hub where folks can share prompts and share chains and sort of be a little bit of an open source hub for some of these language model things. This is very early, but I think at the least, it's really useful looking through the LangChain source code because it has a lot of interesting tips and tricks kind of embedded into it. Okay, very last thing before the end. How do you let's say you are a company and you have a bunch of your own text data, like how do you get it into a large language model? I said, you can only feed so much into the context, so you can't stuff like, a terabyte of text data into the prompt of a large language model. So part of the answer is you could use techniques like fine tuning, but there's a different pattern that sort of emerged that is really useful. And this is, it's sometimes people call it retro, but it's basically combining techniques from search and retrieval with these large language models. And the idea is you start on the left, you have a bunch of your own text data. These could be, documents, things that are in your text in your database, various APIs or whatever, but you just have a giant mass of your company's text data. So the first thing you do is you pre-process that data, you split it up into little chunks, and then you run each of those little chunks through a language model. So actually, I didn't talk about this at the beginning, but one of the other useful things language models can do is output a large vector of numbers, which is called an embedding, that represents a piece of text. So it's not the final layer of the model where it gives you the actual text itself. It's usually an internal layer that represents kind of the meaning of the text. So you take each chunk of text, you convert it into one of these embedding vectors, and you store it in a vector database or a search index or something that allows you to compare vectors to each other. And so the thing about these embeddings is that sentences that have similar meanings often end up very near to each other in this embedding space, and things that mean something very different end up far away from each other. So this is sort of a pre-processing step. You take all your data, you load it into this vector database or search index, and then when a user comes along and they type in a query, the first thing you do is embed that query with the same language model. And then you run some sort of search. You say, hey, give me all of the relevant pieces of text in my database that might be relevant to this question. And you return them, and then you stuff them all into a prompt to the language model. So you tell the language model something like, given the following relevant documents, answer this question from the user and cite which pieces of text you use in your answer. And you stuff in all of the little pieces of text that you found relevant from your search engine. You stuff in the question from the user, and then the language model will generate an answer out the other side, hopefully with citations to the documents that you fed into it. And so this has become kind of all of the things that you see, all the blog posts you see of folks that are like, I wrote, our developer documentation is now chattable with ChatGPT. Like, this is the pattern that people are using, chunking up their text, embedding it, and then doing this search query and feeding it into the prompt. And there's a package, an open source package it used to be called GPT Index. They changed the name to Llama Index. I think now that the Llama model came out, they probably wish they hadn't done that. But anyway, it's called Llama Index now, but it's a framework for letting you basically do this whole end-to-end thing. It's got data connectors that help you connect to like PDFs and Word docs and all sorts of interesting sources of text data. It will chunk them up for you. It will help you call the language models, and then it abstracts away a bunch of these different database backends. So if you have an application like this, Llama Index is totally worth checking out. Okay, so that brings me to the end of the talk. I actually did all right on time. Okay, so I tried to think about how I wanted to sum up this talk, and actually I think like this graphic is maybe the most fitting summary of this. This is kind of what it feels like to be working in ML right now, because I feel like everything is really changing at this kind of crazy rate right now, and it's honestly hard for anyone to keep up. But I do think there are a few things that feel at least like clear to me. The first is that a lot of things that like I would have trained bespoke models for in the past, or my teams would have trained bespoke models for in the past, can now be done pretty well with off-the-shelf large language models. So like a lot of these custom trained natural language processing models, whether they work 90% as well, 95% as well, 99% well, it probably depends on the application. But the thing is that you can do this stuff like instantly. So it depends on your business need, whether you need something that is 99% accurate, but it takes 6 months to do, or whether you can get away with 90% is accurate, but you can do it in a day. And I think there's a huge range of things that can be done 90% accurately in a day, and we're going to see a huge proliferation of that kind of stuff in the next years, I guess. So that's the first conclusion. And if you are an ML person, I think I don't know, it's a little bit of a different situation, I think, than we were in the past, because you can do a lot of stuff now with an API that you needed custom models for in the past. The second thing is, notice I didn't talk at all about I hope I didn't use the term AI too much. I tried not to talk about artificial intelligence, artificial general intelligence. I want to sidestep that whole debate. But like, regardless of what you think about that and whether these things are actually intelligent, I think they're probably not, but forget about that. Like, regardless of all that, what language models can do just technically with text information and what we can build on top of them is likely, I think, to be super disruptive in a good way. Like, how we build on top of and consume text information and what we can do with it, I think is going to change a lot because of what these models can do, even if they're not even if they're dumb, even if they're not smarter than a 1-year-old, like it doesn't really matter. Like, technically, you can build a lot of really interesting things on top of them. I said this at the beginning, but truth and reliability are going to continue to be challenges. I think they're more of a challenge if you work in a very open domain. At least so far, our experience has been in a fairly closed domain on top of smaller data sets. They seem to actually work pretty well. In our summarization example, they worked really, really well in terms of not making up numbers and not making up things out of whole cloth. But it's something that I think needs to be evaluated case by case. And then maybe the last thing I'll say, even though it's like, it feels kind of crazy and it's hard to keep up, it's really exciting. It's a really exciting time. I haven't felt as energized like working in an ecosystem for a long time, because it feels like the stuff is very new. What we can do is expanding every day, and it's just super fun. So that's it. I have one link down here. If you really want to get into the nitty gritty, this is an amazing video on how to code up a GPT model from scratch in Python. It's totally worth looking at. And then I found these in the course of my talk. I'm going to leave this here while I answer any questions. All right. Any questions? Yeah. Sure. Yeah. All right. I suspect it's because this is much easier and it works pretty well. So this is not going to work for every single use case, but I think it's like the easiest thing you can do upfront because it doesn't require any extra labels, right? Like you can literally try it today. You could chunk up your data, store it, run queries against it, and see how this works. So I think it's that like it's a pattern that seems to work pretty well and doesn't require additional stuff, I guess. Fine tuning requires human annotated labels and it's still you might still even need to do something like this even if you fine tune a model. If you fine tune a model, it just makes the text seem more like the text that you're fine tuning it on, and that might not actually be what you want. Like you actually want answers to your questions. You don't want the answer to reflect like the style that the input document was written in necessarily. So, yep. Yeah, okay, so the question was about parameters and like what constitutes a parameter and overfitting, underfitting, et cetera. Yeah, so like technically a parameter here is a weight in the neural network. So, neural networks are basically a bunch of large matrix multiplications and the elements of the matrices are learned. So like each one of those is a weight, I guess. And yes, the same concept of overfitting and underfitting applies here. Though, yeah, so it does apply. And actually like in my model zoo, one of the things I talked about was there's this model called Chinchilla that came out again almost a year ago. And they made the point that actually a lot of the models that came before were significantly undertrained, that you could increase, you didn't need to actually, so their Chinchilla model only has 70 billion parameters. GPT-3 had 175 million. And they said, actually, you don't need to make the model bigger. You can use a smaller model, but train it on way, way more data because you're under training models. And so that was one of the innovations of this model, which is why Llama, which only had 65 billion parameters, could potentially be as good as GPT-3 because they trained it on way more data than GPT-3. So the basic concepts of overfitting and underfitting still apply here. No, I think an underfitted model just, you're not leveraging it as much as you could if you had more data to feed into it, I guess. The whole concept of creativity, I didn't talk about that, but these models have different ways of sampling output from them because they're probabilistic, right? So the next word, you don't always, it's a probability, right? What the next word in the sentence is. And there are different ways you can sample from the model. You can always take the thing that's most probable, right? Or you can sample with some frequency related to that probability. And these models have a parameter called temperature. And as you turn the temperature up, you sort of explore different possibilities more. And that is often linked to like creativity or garbageness, I guess, in your models. So like if you want to do something that is truthful, the advice is to always pick the most probable things. But for some things where you want to like explore, then you turn the temperature up and sample differently in the model. Yep.
Obviously the result. I think like
I actually don't know the answer to your question. And I'm not entirely sure like anyone knows the answer to your question. Like, it probably depends on application by application. Like, so the question was like, if you work with a smaller open source model, if you give it just the right prompt, can it be as good as a larger closed source model? And I think it depends a lot on your application, probably, and how complicated it is. And I don't think there's like a general purpose answer, unfortunately. Mhm. Okay, cool. Man, there's so many questions. I'll just go this way. Yeah. The question was Einstein GPT from Salesforce and Bloomberg GPT from Bloomberg. I have not used either. I've read the Bloomberg GPT paper. So the Bloomberg GPT paper is they trained a from scratch large language model on a bunch of open source text data, but then I think the majority of it was their own proprietary Bloomberg News data. It's kind of interesting. It's actually, I think, the first case of a domain vertical specific one of these large language models I know about. I'm not familiar with the Salesforce one, but they claim in the paper at least that for financial specific tasks, like there were a lot of like headline generation and summarization and sentiment tasks that training a model from scratch on their data set does better. And that makes intuitive sense that it could be better. But how much better is it worth the money and time they spent doing it? How many companies are going to be able to do it? I think that's sort of the open question. And I doubt they're going to let other people use it, but I don't know. I could be wrong. All right. Thanks, Nicole, for asking the hard questions, like always. So the question was the bias that's inherent in these models, and are we concerned with bias in models? So I think generally, yes, that's a concern. I think like what I said towards the end of my talk is that like I think the more open your domain is and the more varied the kinds of things people are going to ask it, I think those are potentially like really valid concerns, right? It's a lot riskier when you just take a model and you open it up to a large group of people on an open set of like literally ask this model anything. I'm hopeful that in our case, like we're working with pretty constrained data sets around like a pretty constrained set of financial questions, that the risks are lower. But it is something I think we probably have to evaluate. I mean, it's like, since we're answering questions largely about companies and company financial performance, I think the bigger risk is like factual inaccuracy. And I think like, although it is a valid point, like if we have non-native English speakers who are in our transcripts, like how the models will handle that. And that's actually not something I thought about, but that's a valid point, I would say. Yeah, so the question was like, do you get any kind of uncertainty out of these models or way to sort of like interpret their output? Generally, no. I mean, one way to quantify the uncertainty is that technique I mentioned, like consistency sampling, like taking multiple samples and seeing how it changes and how the answer might change. That's like one potential way to do it. But you know, like if you're asking it to predict a numerical output or something and you want some sort of uncertainty around that, other than like asking it to give its own uncertainty, I don't know that there's any good way to do that. I mean, you can certainly do evaluation. You can treat it like any other black box classifier. Like if you have labeled data, you can run a test set of your labeled data through the language model and get the answer and calculate an accuracy on data it hasn't seen before. And like you can use that to get some estimate. That's the same thing you would do with any other black box like machine learning model. But if the output is like a more complicated sentence or text or something like that, there's at least not a way I know of to do it. Yeah, the suggestion was like, can you prompt the model to generate its own kind of its own confidence? I think yes, you can try all these things, but whether there's like a principled reason to think that they might work, I don't know that there is necessarily. So much of this stuff is empirical right now, I guess. Like in our summarization models, I tried to be very stern, like with a child in the prompt, like do not make up numbers, like only use numbers that were given to you. And like and so we spent a lot of time actually like pulling out numbers and comparing numbers and summaries to numbers and things and like seeing if they match. And like, it seems like it works pretty well, but like, is that because I was being stern with it and that really worked? Or is that just me anthropomorphizing the model? Like, I don't know.
Well, before we
The question was about AI explainability and did all that stuff disappear? No, I mean, that's like for supervised machine learning, that's still a very active field of research. And if you're doing, credit default risk and loan prediction and stuff like that, like interpretability and explainability is like a huge thing and it's still really important. But here for these language models, I mean, this is one of the, actually I should have mentioned this earlier, but like, if you want, I really, really like Gary Marcus, who writes about he's very critical of a lot of these large language models. And he's just great to read about this stuff, no matter what, if you're critical or if you're a fan, his stuff is really great. That is one of the large complaints. Like, we don't understand exactly why these models are doing what they're doing. And we can't really explain it. And like, that's a problem. And I would argue it's a problem for certain things. Is it a problem for everything? I'm not sure. Also, Garrett, do you want to just tell me when to stop Q&A? I'll keep going. 2 more? Okay. All right. Alex, you can ask me a question anytime. So it was you and you in the back corner. All right. Yeah, so the question was around like, as you build larger and larger towers of these models and like chain together, how do you guarantee the accuracy and understand what's happening on the inside? I think I'd say no one knows the answer to that question. So this project Guardrails is kind of one attempt to get at that question, which is like, it's almost like testing in a software engineering sense, where like it allows you to define a spec and certain kinds of tests that your model output has to pass. And if it fails, there, various things you can do if they fail. And so this is an attempt to like put a little bit more rigor around some of the output. But you're right, as you chain 50 of these things together, it becomes a complicated system. And how do you know if it's brittle? Or, I mean, there also are folks that might argue that like the whole point of deep learning was to learn things end to end, so you didn't have to do these ad hoc things. And now we're building ad hoc things out of them. So whether that will last, I don't know. But yeah, it's a valid point. I mean, that's literally if you use like Bing Chat, or you've seen these videos of people using Bing Chat, like it will start outputting something and then it will erase from the screen because there's a second model that's looking to see if the first model is producing inappropriate content and then like removing the content. So people are building systems like that. Whether it's a good idea, I don't know. But, and yeah, back in the corner. This question was about generating structured output. So I've used a bunch of these cases where I've asked it to input one thing per line with a dash in the front as sort of a structure, and that's worked. What are you doing for your topics? Are you asking it to put one per line as well? Oh, okay, so for me, it's worked pretty well. Alex said he's needed a chunk of regular expressions to kind of clean things up. I do think it tends to work pretty well with like JSON type output because it's seen a lot of JSON in its training data. So, yeah. All right, great. Well, thank you. Are we going to go straight to lightning or take a few minute break?
Yeah, so we'll take a little break here before we do just would